So today we're going to go through how to approximate a classical kernel, which is the wavelet kernel, on a quantum computer. So I'm going to start by just quickly going through what a support vector machine is, and then a variational circuit or parameterized quantum circuit. And then we'll talk about how the structure of these parameterized circuits can affect the functions you learn. And then lastly, we'll go through to actually approximating a classical kernel. So a support vector machine is a form of supervised machine learning. We usually use it for classification. So this is a very simple example of one. So we have two groups of data, the green and the blue. And essentially what we want the support vector machine to do is draw this line between the two data sets so that when we get a new data point, we can decide, does it go into green or does it go into blue? So the way it does this is by taking the furthest outlier data point, or not outlier, but furthest data point in the group on each side, and basically creating this line such that the space between the two data sets is as big as possible. And this method is really nice because it scales up with dimensions. So you don't only have to have two-dimensional data, you can keep up in the dimensions, and then the line you draw ends up being a hyperplane. So this is really nice when the data is linearly separable. But then in the real world, data is not always linearly separable. So when it comes to this, we do something called the kernel trick. So what we do is take our data, so for example, the one on the left, and we map it into a new space where we can draw a line between them. So basically what we would do is map it to a new space where there's a more clear separation between the green and the blue data sets. Then we draw, in this case, a plane between them, and you flatten it down again, and your margin would now look something like a circle around the green data points. And then this technique is nice because you can use many different feature maps to map to different spaces depending on your data set, and you can separate all kinds of data. So this is all done within classical machine learning. It's a method that's used quite a lot. So now we're just going to jump to a variational circuit. So these are hybrid quantum classical computers. So what we have is a quantum circuit, which has a parameterized circuit block, which you can see has the U of theta over there. And then it has an encoding block, which is S of x. It has a measurement, which happens over there. And then we have a classical optimization function. So basically what we do is we have a qubit in the ground state, or as many as we want. And then we use the S of x block to encode the classical data into a quantum state. So there's many different ways you can do that. We'll get into some of them later. But for example, you could rotate the qubit, and that's called rotational encoding. Then our parameterized block has these parameters theta, and these are controlled by the classical machine learning loss function. So these parameters get updated kind of in a black box manner, machine learning stuff. And then we take a measurement of the circuit, and then we feed those results to our classical loss function. So then the classical loss function either keeps going for a set number of steps or until we get sufficiently close to what we were looking for. That's defined when you're setting up the loss function. So these circuits are really nice because we can use them on current day quantum computers, and we can use our known methods from classical machine learning to help us speed up the process, because our current quantum circuits only have a few qubits on them, up to 100 and something. And they've also been shown in some cases to have polynomial speed up over certain machine learning applications. So now what we want to ask is how the structure of this circuit affects what functions can be learned by a machine learning algorithm. And whether we can or can't use this to our advantage, and how we could maybe do that. So to understand how the structure can affect the learning, we're going to look at this circuit, which comes from the paper at the bottom there. So basically, the circuit is kind of two different circuits in one. So you'll see it has layers. So the layers either refer to the repetition of the W and S of X gates. So W, 1, 2, 3, up to L, which is number of layers, or it means the layer is how many qubits are used. So if it has multiple layers, you'll only be acting on a single qubit. And if you have multiple qubits, you'll only have one W gate and one S of X gate. So the S of X gates are the encoding gates. In this case, it was rotational encoding. And the W1 gates are, well, W gates are the parameterized circuit blocks. So the reason that this circuit was interesting is if we go here to the results. So the researchers tried to approximate the function you can see with the dotted lines, the dots on the solid line. And so the first circuit in blue is when we have just a single qubit with a single W gate and a single S of X gate. And basically just learned a sine function. Then if we add either two more encoding blocks and parameterized blocks or two more qubits, you can see it still doesn't really learn the function well, but it's a much better attempt. And then if we go to 5 qubits or 5 repetitions, it seems to do quite a good job of learning. So this is interesting because we see as we increase the number of qubits or layers in the gate, we can more accurately learn the function. And it seems to be following a Fourier series. So we seem to be adding a term to the Fourier series every time we add a qubit in. And this technique of doing it on a single qubit with repeated gates, it's called data re-uploading. So just a term for that. So now, yeah, so this is the thing to take away. So the frequencies of the Fourier series are determined by the encoding gates, the S of X ones, and they correspond to the eigenvalues in your rotation Hamiltonian. But very technical stuff, we don't need to get into that right now. And then the Fourier coefficients themselves, so how strong each sine function contributes to the overall function, those are determined by the parameterized gate. So in this case, our classical algorithm, the loss function, is deciding how much each sine function contributes to the overall learned function. And the setup with the encoding gates is determining the number of frequencies we have access to. And then the other interesting thing was these results were basically recreated in a paper which aimed to create a quantum analogy to a support vector machine. And that's the paper at the bottom. Also, if there's any questions at any time, please just stop and ask. So now, well, we can make an argument from this that the structure of a variational quantum circuit is basically a kernel method inherently. So the logic kind of goes, we have classical data, which is what we're feeding into our quantum circuit. And the process of mapping that to a qubit is basically, it's mapping it to a new space, which is what our support vector machine kernel method does. And then once we're mapped into this new space, which is our quantum circuit, we're doing a series of unitary operations on it. So it's all just linear algebra, which is what the support vector machine does when it's mapped into a new feature space. And then when we take a measurement, we're mapping back to not exactly the original space in every case, but mapping back to a simpler space. So overall, we're kind of, the supervised learning method is basically doing a kernel method. And that argument is much more well laid out in that paper listed at the bottom. So basically from that, we can say that every method of encoding is linked to a kernel, and So these are just three very popular methods of encoding. So basis encoding, basically just that you have your string of binary like 1, 0, 0, 1, and then you have 4 qubits that you map to 1, 0, 0, 1 or something like that. So that would create a delta function kernel, which is basically just 1 if it's the same, 0 if it's not. Then amplitude encoding would create this kernel, which is basically just magnitude squared within in a product. And then rotational encoding is what we're going to look at because it's quite commonly used in a lot of variational circuits. And the other papers we've looked at already, they used rotational encoding. So it creates this kernel. So what we want to ask is how we can explain why a single qubit circuit only learns a sine function. So we're going to have to define a lot of mathematical terms. I won't get into all of it hectically now because this is just an explanation, a rough explanation, and it's a lot of math. But essentially, we have this phi as our data encoding feature map, and we can get rho of s, which is our density matrix from that. And then a quantum kernel is defined as the trace of the two density matrix and the inner product of the feature map. So what we're going to look for is a way to explain why this rotational encoding ends up only learning sine functions. So the way we're going to do that is we know that the eigenvalues determine the frequency. So we're going to basically look for a way to determine the eigenfunctions. So to do that, so yeah, this is the rotational encoding in 2x2 matrix form, and then the density matrix it creates. So x can be any value really. It's just saying how much we're rotating our qubit by on the blocks here. So we have to define this integral operator. And so the second point here is the RKHS, which is the reproducing kernel Hilbert space. Basically, that's a lot of math that we also don't have to get into right now, but it's basically trying to define the family of functions that make up the space. So if you think of it in terms of the Fourier series, the basis functions of that are all sine and cos functions. And that's what the reproducing kernel Hilbert space is made out of. So basically, we take these two things and we solve by plugging in all of this. If you really want to see the solve and the proof, I'll show it to you afterwards. 2 or 3 pages, so we won't get into it now. But when we solve for this, we find that the eigenfunctions are basically this over here, which is a cos function, which is shifting and scaled, which would then explain why a single qubit going through rotational gates can only learn a cos function, because the eigenfunction of this space is a cos function. And when we're trying to learn with this circuit, anything will be biased to learning. So it will be biased to learning in the form of a cos function. So the closer we are to a cos function, the more accurately it can learn that function. But the thing that's nice about this is that the cos function is what makes up the Fourier series. And we know that if we have enough terms in the Fourier series, we can actually approximate any function. So from this, we can basically say that if we add enough terms or enough qubits to the circuit or enough repetitions of the encoding gates, you could approximate any function or learn any function to a certain degree at least. So from here, we have, using what we've done, we also now have a framework where we could take any encoding method and work out the eigenfunction for it, and basically say how any encoding method will bias the functions which you can learn. So that's nice for if you have just an encoding method, you want to know what types of functions it will be good at learning. And yeah, so now we want to ask, okay, sorry, the other thing is, so in the previous examples, the rotational encoding only added one term to the Fourier series each time you added a qubit. But there are other encoding gates, such as this one, which actually exponentially increase the Fourier spectrum. So instead of having 2 qubits giving you two terms in the Fourier series, you now have this expression here. So it's at best up to like 3 to the n. In the examples we used, it was 2 to the n. So if you had 2 terms, you'd have 2 to the power 2 terms in your Fourier series with 2 qubits. So these are, so the beta mn is just, it's a big expanded term that's being compressed. It's basically just, yeah, trying to compress a whole bunch of eigenfunctions into one exponential instead of having it stretched over multiple qubits and taking a tensor product of all. Now we basically want to ask, so it's quite easy to have a kernel function, but it's not so easy to just have a kernel function and know which feature map and encoding method would give us that kernel function. So in the support vector machine example we had, we used a Gaussian kernel to map the center up and the blue ones at the bottom outside. So initially I tried to basically start with the Gaussian kernel and basically do that process in reverse to try and find an encoding method that would exactly implement the Gaussian kernel. And it turns out that that is a very non-trivial task. So instead, we're going to approximate any classical kernel on a quantum computer using what we've learned here. So there was originally a tutorial up on Penny Lane, which was, it's basically a library for coding quantum computing things in Python. It's very useful. So on their website, they had a tutorial for how to approximate a Gaussian kernel. So I basically took this tutorial and tried to break it, like a good student. So they used the Gaussian kernel, which is a nice hump shape. I'm sure we're used to it. And I decided to use a wavelet kernel, which looks like this. So it's very similar, but you can see it has dips on either side, and these are usually negative. So now I'm just going to take you through the process of how you could take any function that fits these parameters and approximate it with a quantum circuit. So you select a kernel function, and you just have to make sure that at k of 0, the kernel is equal to 1, and that the function is always positive. So for the wavelet kernel, those 2 dips on the side are usually negative. So I shifted the whole kernel up and then scaled it down so that it met both those requirements. And then we're going to repeat this one. So we're going to periodically extend it. So what that looks like is this. And the reason we're doing this is just to make it easier to take a Fourier series of this function. So the next thing we need to do is find the Fourier spectrum and then decide how many qubits we actually need to accurately approximate it. Accurate is very dependent on what your use case is. Some things you're going to need a much more precise approximation, some things you can get away with it more general. So if we decompose this, this is the first 32 terms of the Fourier spectrum. And as you can see, basically from number 5 onwards, it's significantly smaller. So that tells us that the first 5 to 6 terms of the Fourier series dominate the Fourier spectrum. And the nice thing about this circuit that we're going to use is that we have an exponential Fourier series with the qubits. So we need 2 to the n qubits. So if we need only 8 terms of the Fourier series, we only need 3 qubits, sorry. But because this was a relatively easy circuit to run, we actually just went with 32 terms, which was 5 qubits, which is still not very resource intensive. And 5 qubits seem like it should be achievable on a physical quantum computer as well. So these will all run on a simulated one. So this is the quantum circuit we construct to approximate it. So it's actually relatively simple. So S of X is our encoding gates, and these values are specifically chosen so that we have an integer Fourier spectrum. So if you remember from the previous example, the encoding gates determined the frequency values of the Fourier spectrum. And these WA1s, so previously the parameterized gates had theta as like the free parameter. In this one, it's called A because the A stands for amplitude, and then we use that to calculate the probabilities. And so it's just a more intuitive label. So the WA gates are a bit different from all the ones we used previously. So it uses Montonen state preparation, and that's defined by that function there. So you take a qubit 0, you apply the unitary to it, and it produces that state there. Basically, what it does is it's a sequence of controlled rotations determined by the values A, which are the amplitudes. And so a uniformly controlled rotation on a qubit is composed of all possible controlled rotations on a qubit. So basically what we do is at this point specifically select the A values so that the circuit, when it runs before we've done anything to it, creates a function that looks like 1 over magnitude x, which is kind of like that shape. Yeah. And then, so if we take this circuit and work out what the kernel we have, we're left with this. So if you notice the x1 and x2, we change into one variable delta. So basically, it doesn't matter what our 2 data points are that we're taking the kernel between. It only matters the distance between them. Yeah. So now, before we run, so usually what you would do at this point is just run into a classical loss function and just try and optimize these A values till you get the shape you're looking for. But they attempted to avoid the black box problem in a small way, at least. So we're going to predict the Fourier spectrum beforehand. And so we worked out the Fourier spectrum before, and we've set these A values. And the reason it's 1 over x is because we know the general shape of a kernel. I think that we'll be able to bend that shape into an appropriate kernel from where it is, and we should be able to find the answer. So we're going to use the classical loss function to do that adjusting of the A values. And the way we adjust it is using this relationship. So we define probability as that there, so the square of the amplitude. And you're able to relate the probabilities to the Fourier spectrum. So each term here is each term of the Fourier spectrum, right? So in our case, it's going all the way down to 32 terms. And then if I just jump to the next slide quickly. So then what we do is S on the right is the Fourier spectrum we got from decomposing the periodically extended wavelet kernel. And the one made up of the probabilities there is what the actual Fourier spectrum is of the function coming out of the quantum circuit. So we're basically just subtracting the 2 at each term and trying to line them up. So we use Newton's method to optimize them. And so yeah, so at this point we run the quantum circuit and we can see what the results are. So these are the Fourier coefficients it learned. So it's a logarithmic scale on the left here. So for the first 5 terms, it learned them quite accurately. And you'll notice for the 6th one, there just isn't a data point. And the 7th one, there is some difference between them. So this was the part that confused us quite a lot. And so basically what had happened is the circuit was actually unable to approximate negative Fourier coefficients, only positive ones. So that actually came because of this gate here, the Martin's state preparation. So because we had very small amplitudes, and when we define probability, we took the square, absolute square of these amplitudes, we actually lost all negative values and all values below a certain threshold. So when it came to the Gaussian kernel and stuff, it actually worked fine because there were only positive values in the Fourier series. Whereas here, because we had 2 negative regions, we weren't able to approximate them. But interestingly enough, when you look at the actual function that was approximated, they're basically the same. So even though we weren't able to approximate the negative coefficients, the positive ones dominated the Fourier series so much that it was actually accurate for a lot of use cases. But it shows that there's maybe a weakness in this method because we just kind of got lucky with this choice. But it also comes down to your kernel choice. So if you know you're using a kernel that has no negative Fourier coefficients, then this method works great. But otherwise, it's not so great. And yeah, so we basically, to evaluate how accurate the approximation was, we basically took the data points at each point on the wavelet kernel and then the approximated one, and then mean squared error. And over all the sample plots, it was times 10 to the minus 9. So if your numbers are on any scale bigger than that, it should be an accurate enough approximation. Yeah, but in the end, we're left with a tool where you can actually approximate a large family of kernel functions on a near-term quantum computer. But it has yet to be run on a physical, but in theory. Yeah, so any questions?
You said there was a proven polynomial speed up for some variational circuits.
Yes.
Can you give me an example?
So basically, it was just specific. It was like very specific circuits. Just had. I'll send you the paper exactly. But they basically just had a speed up. But so a polynomial speed up is not a great one. So it's just for the specific question you were able to run. So that one, I believe it came from basically a derivative of Shor's algorithm, the problem.
You said each encoding gate is a different spightening space function?
Yeah, it adds one to it. Yeah.
And the one that you should use is dependent on what your target function is. So that works if you know what function you're trying to approximate.
Exactly.
If your point cloud is, if you input some point cloud on an unknown distribution, how do you decide on which?
Exactly. So that's the problem with machine learning, right? You can't know what you're trying to learn before you learn it, right? Yeah. But the kind of nice thing is that because it's a Fourier series, you can technically approximate any function.
So you always use the,
as long as you have enough terms, so enough encoding gates.
Yeah.
But again, like how many is enough?
So because the eigenspace function of the rotational encoding is closed line.
Yes.
So
So
good for Fourier, use Fourier approximation for any function. You don't know the fundamental.
yes. Yes.
Because of the.
So yeah. So it may not be the most efficient method or best, but it should work. But yeah, this also kind of all goes to show that it's quite hard to search for new quantum like speed ups or advantages in like quantum machine learning because the data is unknown and what you're looking for is kind of unknown. So it's maybe not the best field for searching for new things, but implementing the current things we do know. Yeah. Well, so if I used like just the one used in the previous example, it could learn the function. But then the problem with that is you don't really know what's happening inside the circuit. So we were trying to do it in such a way that there was as little of a black box as possible. So that was the best attempt at trying to figure out a way where we knew exactly what was happening at every point in the quantum circuit, at least. But yeah, I was trying to find a better one, but I didn't think of one yet.
On that slide where you said 16x, 8x, whatever, that one. What exactly does that mean?
Yeah. Okay, so those are the encoding gates, right? So basically, your first qubit coming in is just you encode just the x value. The one above it, you multiply 2 times the x value, which is 4 times 8, and that just generates a integer valued frequency spectrum.
X here is what?
It's your data that you're feeding into your input vectors for your machine learning.
Yeah, but for your problem, what is?
So it was the x-axis of, yeah, so it was broken up from, I think, between negative pi and pi and 300 points, I believe. So yeah.
And when you measure knowledge, you measure the use. Do you span a computational base? Or do you
Computational basis.
use a project?
No.
So it wouldn't make sense because you said the problem is numbers negative. You have to split the kernel positive and negative, and if you separate it through, and at the end, you add it again.
It could work, yeah. Yeah, probably would. I think the problem was more just with the choice of WA, because you could easily make a circuit that can learn negative Fourier coefficient. So I think it would be better to find the right choice than to try and like force this one to work.
The people online. But then that one people just the people just deleted some of that. That's why I asked Ben to go on the screen. And sometimes in Italy. Oh, I see. You guys, you have questions.
Do you have other questions you can ask me afterwards too? They're not directly related, yeah.
Okay, maybe then let's finish the formal part.
Okay.
Yeah? So, Rivan, thank you very much again, and good luck with your PhD journal.
Thank you.
Keep us posted, and you can invite you to many more.